Sorry? Oh, yeah, I understand. Don't worry. First of all, I want to thank the organizers of this conference for inviting me. It's been a lovely meeting in a lovely place in honor of a very nice man. Over the last 30 years or so, I've had two wonderful international collaborations. One with Helmut Rauch and his group in Vienna, Austria, and the other one with Tony Klein and his group in Melbourne, Australia. I should say Tony Klein and Jeff Opat, for those of you who remember Jeff. Actually, we began as competitors when we were all chasing the same minus sign. As you may know, if you take a neutron, which is a spin 1/2 fermion, and let it precess, say, in a magnetic field through 360 degrees, the sign of the wave function changes. And this fact is deeply embedded in quantum mechanics, but it had not been directly observed experimentally until 1975. It was observed for the first time nearly simultaneously and independently by each of our three groups. In Klein's case, it was done by wavefront division interference across a ferromagnetic domain boundary. Experiment was done in ILL. In Rauch's case and in my case, it was done using perfect silicon crystal interferometer that was invented of the type that was invented by Ulrich Banza and Michael Hart about 10 years earlier for X-rays when they were both postdoctoral fellows at Cornell University. I'd like to begin by telling you how this device works for neutrons, but as an aside, I should remind you that Aharonov and Susskind had suggested in 1967 that this famous minus sign might be observable by electron interferometry. Herb Bernstein suggested looking for it by neutron interferometry at about the same time. An appropriate interferometer of either type did not exist at that time. Oops. How do I go back here? Previous. Boy, this is... So here's a schematic diagram of the Banza-Hart silicon interferometer, and also there is a picture of one there. It consists of 3 upright silicon plates attached to a common base. It's called an LLL device because it has 3 Laue transmission geometry plates. And here is a model of one. Actually, it's a model of the interferometer that is the picture of. This is a model. And if you like, you can come up later, get your picture taken with the interferometer that belongs to Sam Werner. This one's made of aluminum. It feels about the same as the silicon one. Of course, the silicon one is very valuable and very fragile, so I don't bring those along. But this is the same size as the one that's there. So if you like, you can come up, have your picture taken with it, take it back home, and tell your friends that you had one of Sam Werner's neutron interferometers in your hands. No one would know, and it feels about the same. So how does it work? Suppose you have a nominally monoenergetic neutron beam. Let's say has a de Broglie wavelength of about 2 angstroms, and direct it toward the first crystal plate, toward point A on the first crystal plate. And let's say at an angle which corresponds to the Bragg angle of, the 220 Bragg reflection, which was in fact the case for this interferometer. The two outgoing beams that leave the first crystal plate will be coherent because the crystal is a perfect crystal, and will automatically satisfy the Bragg condition in the middle crystal plate. In the middle crystal plate, two of the beams that leave those 2 points B and C and are directed toward point D in the third crystal plate will mix and interfere and have two outgoing beams which go into two detectors, which I label C2 and C3. These are helium-3 gas-filled proportional detectors, which have essentially 100% efficiency for detection of neutrons. So, the scale of the interferometer you can see there is about, 10 inches? 10 inches? 10 centimeters? We have some that are, let's say, 20 centimeters in size. So here we have it. Here we have a matter wave interferometer operating over macroscopic distances with the Broglie wavelength neutrons of 2 angstroms or so. If I change the relative phase of the two beams traversing the interferometer on, say, path 2 versus path 1 in that diagram, by rotating that phase plate, that phase rotator, quite often it's a polished plate of aluminum that's 2 millimeters thick. That's all I do is rotate it, increase the index refraction path length on one leg relative to the other leg. If I do that, the counting rate in the detector, say C2, will go up and down, up and down, up and down. Well, the counting rate in the detector C3 will go down and up, down and up, down and up, 180 degrees out of phase. That is, we're conserving the number of neutrons coming out because the silicon interferometer absorbs no neutrons. So what's happening here is I vary the internal phase difference on path 2 relative to path 1. The neutrons are being swapped back and forth between detectors C2 and C3. We do that almost every day. But, people that come to the lab and see what we're doing it's kind of amazing that this is happening. Of course, this is sort of the magic of quantum mechanics right before your eyes. Here is a pair of interferograms. They were taken recently at NIST. Shows a contrast or fringe visibility of about 88%. Here I call the C3 beam the O beam, the C2 beam the H beam. That's a matter of nomenclature. Note that the two interferograms are 180 degrees out of phase with each other. The sum is a constant as required by the conservation of outgoing neutrons. As I say, the silicon interferometer does not absorb any neutrons appreciably. Okay. Suppose now that I thread a line charge of density lambda through a closed loop created by the beams in my neutron interferometer as shown here and as envisioned in 1984 in the paper by Aharonov and Kasher. If the line charge is along the z-axis and the neutron is polarized along the z-axis, the canonical momentum has an additional part, which is mu cross E over C, which I show there. If mu, the magnetic moment, is along the z-axis, then at mu cross E, because E is radially outward from that line charge, is a solenoidal vector field, just as the magnetic vector potential is in the usual AB effect. Here again, there is no force on the moving particle. The moving particle in this case is neutron carrying magnetic moment mu, and I again say polarized along z-axis. One calculates the phase shift by taking that canonical momentum, which is easy to get from that Hamiltonian. It has this mv plus 1 over c mu cross E in it. Integrate that canonical momentum around the loop. I show there, and you get the famous, now famous, Aharonov-Bohm phase shift formula. In that formula, sigma is plus or minus 1, plus 1 for spin up, minus 1 for spin down. Mu is the magnetic moment of the neutron, lambda is the line charge density. This phase shift is independent of where that line charge threads the loop. That is, it's topological. So if you take that seriously, we might just as well thread the loop with 2 line charges and double the effect. With 3 line charges, triple the effect. 1,000,000. Well, if you have 1,000,000, that's like an electrode, say a charged electrode, say a charged rod threading the loop. These ideas lead to an experiment, which I now show. So here is our silicon interferometer. The silicon plates are colored in blue. The charged metallic electrode is outlined in red. The lines of electric field radiating from the charged metallic electrode in the center must end somewhere, and we choose to let them end on a negative electrode just outside of the loop, outside of the beam path. I show the calculation now on the top, which I've written in, what the magnitude of the expected results for the AC phase shift would be in this experiment. Using Gauss's law, I can, from the electric field, which is the potential divided by the gap distance, lambda there, I get formula in terms of the high voltage potential on the central electrode divided by the gap. The result is 1.52 milliradians. That's what the theoretical result is. That's a very small phase shift. Those of you who have done interferometry in any context, that is a very small phase shift. How to measure such a small phase shift? First of all, we must set the spin-dependent phase shift to a point of maximum slope on a spin precession interferogram. Using the small adjustable magnet, which I've colored in green there, do a spin precession interferogram to say sinusoidal spin precession interferogram and set at the point of maximum slope. Then we'll turn on the electric field. In our case, it's 45 kilovolts over a gap of 1.5 millimeters. Count neutrons in the 2 detectors C2 and C3 for 10 minutes. Reverse the polarity of the electrodes. Count neutrons again in the 2 detectors for another 10 minutes, and finally turn off the high voltage. Count neutrons for another 10 minutes. It's a 30-minute cycle. Repeat this cycle 10,921 times over a period of 2 years. Okay, I show here a spin precession interferogram for both the C2 and C3 detectors. Note that they're 180 degrees out of phase with each other, indicating again the conservation of outgoing neutrons. If we set the magnetic field to a point there on the abscissa of about 56 Gauss, that's the 3 pi over 2 phase shift point, we're at a positive slope, as the interferogram C3 has a positive slope at that point. Switching the electric field on makes the C3 counts go up a bit because the AC phase shift is a spin-dependent effect. Actually, only 1 part in 1,000. Switching the field to negative, that is reversing the polarity of the central electrode, makes the C3 counts go down a bit on average, up of order a part in 1,000. If you know the slope of that interferogram, that is at that point, which is green, I don't know if you can see that green from where you sit, the operating point, that's the inflection point. If we know the slope at that point, we can convert then a difference in counting rate for for central electrode positive minus the counting rate for when it's negative into a phase shift. That is, if we know the slope, we know the counting rate, plus and minus, we can convert it into a phase shift. That is on the axis, on the abscissa. This is what we call phi sub AC. That's the AC phase shift. That's the number we're looking for. That's a number which theory predicts for this experiment is 1.52 milliradians. Our AC experiment was done with unpolarized neutrons. How do we see spin-dependent effects with unpolarized neutrons? Well, there are two types of phase shifts. One is spin-independent. I'll call that alpha in these equations below. And the other one is a spin-dependent phase shift, which I call beta. So for spin-up neutrons, the interferogram, it's a sinusoid, it has the form of A plus B cosine alpha plus beta. For spin-down neutrons, it's A plus B cosine minus beta. For unpolarized neutrons, assuming that the neutrons that come out of the reactor and down from the monochromator are unpolarized, which turns out to be a very good assumption, that you add spin-up plus spin-down intensities, and you get this nice formula, A plus B cosine alpha cosine beta. Cosine alpha cosine beta. Okay, so this means then, knowing that, we must set the phase, alpha, that's the spin-independent phase, to be, say, 0, pi, 2 pi, or so on, to make cosine alpha, say, 1 or minus 1. So we get the maximum effect. We did that with gravitationally induced quantum interference. Now, we could have done it with putting that aluminum phase flag in this interferometer, but it's a fairly small device, and there just simply wasn't room in the interferometer for this aluminum phase flag. So we just tilted the interferometer by a small amount about the incident beam using gravitationally induced quantum interference, sometimes called the COW effect after the authors of the original experiment. Okay, so we set then alpha to be 0. And we set beta, that's the spin-dependent phase shift, from the spin precession interferogram to be either pi over 2 or 3 pi over 2 to select whether we want a positive slope operating point on the precession interferogram or a negative one.
Hurry up, Sam. Hurry up.
Hurry up. We'll have another 15 minutes.
No, you're speaking too slowly.
He knows what my extra slides are, and he would like me to show some of his extra slides. And we have some. We'll see.
There's another speaker after you.
So it's very important here that this experiment was done with unpolarized neutrons, because phase variations due to vibration, temperature variation, pressure, so on, affect the spin-independent phase and not the spin-dependent phase. Okay, so stability on the spin-dependent interferograms is quite high for unpolarized neutrons. Okay, I show here. Here is a series of magnetic scans taken at different interferometer tilt angles. That is, the gravitational effect on the relative phase of the beams is different. That's why I'm varying the tilt angle. On the right, gravity scans for different magnetic fields. So you go through this whole series of scans, and you find where the setting points are, where the operating points are. And I show where those two pictures, panels, where the phase goes through pi over 2 to set accurately the operating points. Okay, I now want to tell you what the final result is, okay, of this AC effect experiment. The result is given down below. It's 2.11 plus or minus 0.34 milliradians. That's a 1 sigma statistical error bar on that data. I show also the table of data, this difference data, a table of difference data. I don't expect you to reach any sort of understanding of that at any level very quickly, but I do want to make some comments about it. Repeat, the experiment was done over an extended period of time, over 2 years. The data was divided up into 2 major segments, 1 and 2, which you can see labeled in this table. The reactor's beryllium reflector was replaced in the middle between segment 1 and segment 2. The data was further divided into 3 parts depending upon whether we were at the positive, negative, or 0 slopes of an interferogram. The total of 10,921 cycles, 30 minutes a cycle, you can multiply that yourself. That's something like 5,000 hours of data taking time. The counting rate due to the application of the electric field, as I said, was about a part in 1,000. The total number of neutrons counted in the interferograms was about 100 million. Less than 10% of all the data that was taken was discarded due to reactor scrams, electrical outages, or electronic malfunctions. And finally, again, I say it was really important that the experiment was done with unpolarized neutrons as opposed to polarized neutrons. Okay, this is the first measurement of the AC phase shift that I am aware of. Maybe the only measurement, direct measurement, as of right now. Okay, Klein wants me to hurry up here. I know he has other agendas here, but I want to talk a bit about the scalar AB effect. Now, you've already seen the diagram of the panel, the top panel, a number of times already in this conference for electrons. But let me say in my language so that you will understand the bottom panel in my language. Suppose you have an electron beam which you divide at some point and let one part goes through on path 1, another part goes on path 2, but they go through metallic cylinders, say with a pinhole on either end to let the electron come in and out. One is a bias potential, the other is a pulse potential. So suppose I pulse the potential on while the electron is inside of the lower Faraday cage. The electron will feel no force because it's inside of a Faraday cage. But nevertheless, there will be a phase shift. That's due to the change in the potential, and the formula is written there. And this, basically, this drawing is in the original Aharonov-Bohm paper. To my knowledge, this experiment has never been done successfully. That is, without any force-connected effects from the Faraday cages placed in an electron interferometer, because of the small sizes that are involved. However, we have observed this an analogous effect with neutrons, which is shown schematically on the bottom panel. The idea is the following. When neutron wave packet is on path 2 and is inside the pulsed solenoid, that's the bottom solenoid, which is a relatively long solenoid inside of the interferometer. We pulse the magnetic field on for 8 microseconds. It takes, for our experiment, it takes 25 microseconds for the neutron to go through that, to traverse the solenoid. The magnetic field within the solenoid is uniform to about 1%. After 64 microseconds, magnetic field is pulsed negatively. The cycle is then repeated many times. And by time of flight detection, one can tell whether a particular neutron was in the coil when the coil was pulsed on. That is, we have detectors placed at a certain distance away from the interferometer, and when they arrive at the detector, we know then when they were inside of the coil. So you do by time of flight. You can tell whether the neutrons were in the coil at the time when the pulse was turned on. Okay. When they're inside the coil, it's a long solenoid, and the magnetic field comes up. And neutron magnetic moment feels that magnetic field, but there's no gradient, spatial gradient, so there's no force on the neutron. Magnetic field mu b2 integrated over a pulse time of 8 microseconds, in our case, gives a phase shift, okay? And it's shown down below. So it's in complete analogy, as far as I can tell, with the electron case. The original idea for such an experiment was proposed by Zeilinger in 1985 and by the late Jiva Anandan in 1987. This experiment was done also with unpolarized neutrons. It was done with a skew-symmetric interferometer, and it caused some what I would call quantum confusion amongst certain theorists. 5 years later, we decided to do the experiment with polarized neutrons, longitudinally polarized neutrons. The results are the same, and the results are quite beautiful. Here they are, polarized, unpolarized, scalar AB effect. Now, if you want to learn a little bit more about this whole subject,
Sorry, we haven't got time for the
here's
commercials.
book.
Sorry, we haven't got time for the commercials, otherwise I'd say...
Tanimura could advertise Hitachi. I can advertise my book. This is Neutron Interferometry. It's Lessons in Experimental Quantum Mechanics by Helmut Rauch and myself. 40 experiments, 1,200 references, 400 pages. Cost is $100. Fantastic investment.
Thank you very much.
And the illustration on the cover, this is what Klein wants to say. He's trying to stop me from saying this so he can say this. The illustration on the cover is due to Charles Adams. It first appeared in the New Yorker magazine in 1940. Klein likes to call it the Charles Adams effect, the CA effect for short. It's never been observed. Thank you.
I'm sorry, we won't have time for any questions. You asked them in private, but just one comment from the chairman. People do beautiful experiments of this kind, and then along come the theorists and quibble. So I have one additional slide. Would you like to show that, please?
See, we knew that there was time left, didn't we? These are time of flight data, where the experiment was done. This is the reactor at Missouri at NIST. No force. All right. This is your turn, Tony. Go to it.
This is a special for the theorists to quibble about such things. Now, we have one more speaker. I'm sorry for running out of time.
Tony, you have to get up on the stage.
No, I don't. I just have to speak so they can
Fine,
hear.
I think we can have one. We can manage one or two questions.
You have a question?
Yeah, we can manage one or two questions.
I'll stay here. You speak loudly.
Any question? Yes.
In the original experiment, how do you shield the neutrons on the charged pilot?
They go. It's not a. So say it's a line charge for simplicity. Okay, the electron is a line charge. So radioelectric field coming out from that, neutrons going past that, and feels that it's there. There's phase shift from the spin orbit coupling. So you don't shield the electric field. It goes. The origin of the AC phase shift is moving in the electric field. Okay, it's moving in the electric field. Okay, no shielding.
They can't touch the pilot.
What's that?
Physically, they can't touch the pilot.
Oh, you mean the neutrons going through that doesn't do neutrons that touch the electrodes on either side are lost to the interference. They'll scatter out and they don't contribute to the interference. So in some ways, the gap, which is 1.2 or 1.5 millimeters in our case, forms the beam width going through the interferometer. Okay, so the neutrons that go through the interferometer go through that gap. That's how it's done. Okay, so the ones that are close and hit the electrodes, that they don't have any. They're lost to the world. Okay, other questions?
Professor Kepler has a question there.
Yeah.
So, why did you do the experiment with the unpolarized neutrons as long as it was only theorists splitting it?
All right. Well, let me say it this way. We did the experiment with unpolarized neutrons first because it's much easier to do experiments with unpolarized neutrons. Let me finish. take about a factor of 5 in intensity. Doing it with polarized neutrons, you have many problems because of phase drifts and things like that. So doing it with polarized neutrons is much more difficult, and especially with longitudinally polarized neutrons, polarized along the axis of the pulse coil. Why did we do such an experiment? Theorists were quibbling with this at meetings, in papers, and so on. But I would like to, Klein has got to give me time for this one little comment here. One little comment. This is for Tony Klein's benefit, I think, too. In every respect that I know of, this is a force-free phase shift. This is for your benefit, Murray. All right. It is torque-free. It is non-local interferometric effect. It is dispersion-free and non-dissipative. This experiment is AB in spirit and in fact. Now, you can ask.
The point is that the original unpolarized experiment, you can think of it as 2 experiments running at once. One for spin up and one for spin down, which is a mixture of things that come out of the reactor, and each give the same result. So why not do both at the same time and save yourself a lot of trouble? But then, because of the trouble that they caused, they went enormous lengths to polarize the neutrons, to filter out the wrong polarization state, and so on, and eventually ended up getting the same result. And they didn't put my name on that paper. I wasn't in favor of doing it.
Well, you didn't do any work on it.
Well, that's only fair enough. Yes.
So here are the interferometers with the beams, if you would like to come up and how they go through. Take a look at it.
I understand that are polarized neutrons for scalar effect. And for AC effect, the only experiment, as you said, was with unpolarized.
Yeah.
Right.
So you say that it's direct AC effect, but it's almost direct.
Oh, it's a
AC conceptually, we need polarized neutrons.
well, the theorist.
So there is a way to.
Yeah.
I'm persuaded it's good. But
Right.
I think it would be nice
Well,
to have a demonstration of AC effect. It's polarized, so it would be exactly AC effect.
But it was polarized. It was polarized up and down at the same time, different neutrons coming in, and they give the same answers.
Who I think who is giving this talk, Tony? Is it you or me? I would say, let me answer your.
In this way, the exponentiation is zero.
Let me answer your question in a scientific way, if I might. First, okay. The unpolarized neutrons are coming into the region of the electric field, and and they see this motional magnetic field, which forms the axis of quantization. V over C cross E is the axis of quantization. In fact, in that experiment, so I have this crazy slide up here. I can't go back to this other one. The axis of quantization is actually formed in this experiment from the leakage field from that little magnet in there. Leakage field comes back up and is in the Z direction. So in the region of where the neutrons are going through the electrostatic cell, the axis of quantization is in the Z direction. The axis of quantization is in the Z direction. A neutron has 2 states, spin up and spin down. Spin up neutrons propagate separately from spin down neutrons, okay? We went through this little thing already, right, with the earlier on. If you add spin up, the phase shifts in the interferogram. So, in the AC formula, there's mu, sigma plus or minus 1. Plus 1?
I'm
Minus 1.
persuaded that
Okay, well,
it is satisfactory.
Right.
But it will be nicer to have it with polarized, so it's
Yeah.
very difficult.
Infinitely difficult. Infinitely more difficult.
Not
And infinitely.
Sam, it would only take 200 years instead of 2 years.
All right.
Okay, thank you
Is it
very
okay?
much. Right.
Anyway, you can come up if you like. These are available to look at if you want to come. And Klein has a camera. You can have your picture taken with one of my interferometers in your hand. Take it home. All right? Take the picture home, not the interferometer. Okay.